Hi, I'm Kathleen Sibular, and welcome back to another AP Chemistry video. Today we will be looking at Unit 8. So, our first question is about this Ka question with the acid HClO and CH3COOH. Alright, our question is determining the amount of determining the solution with the lower pH, and we are given a 0.1 molar solution of HClO or a 0.1 molar solution of CH3COOH. Okay, since they do have the same molarity, we will be looking at the Ka values, and we have to check which one has the lower Ka value, because having a higher Ka means having a higher pH. So 2.9 times 10 to the negative 8 is a lower number than 1.8 times 10 to the negative 5. So our answer would be CHLO. Alright. Next, we will look at part B of this same question. Which solution has a higher percent ionization of acid? A 0.1 molar solution of HClO or 0.01 molar of HClO? We do this by first using the equation with HClO and H2O, which is acting as our base in this situation, which we could also write as OHO. So the acid HClO plus H2O is in equilibrium with ClO minus plus hydrogen 3 oxygen. Alright, since a liquid, it doesn't count, so we are not counting H2O, but we do have the molarity of 0.01 molar. So I did two different equations, and we did X on the reactant side, and on the products we did plus X. You can see that on both. All right, next we bring it down, and we have, I guess I forgot to write minus X here. So we have the same equation, which we take our Ka, 2.9 times 10 to the negative 8 is equal to X squared over the molarity we're given minus X. And X is a very, very small number, so it is negligible. So we don't count it on either equation. So how we do this, we'll times this number by this number so that we get X squared alone. And we do that for the other side. And then we square root it to just get X by itself. And our X value is 1.7 times 10 to the negative 5, which is our H3O, or it's our ClO minus, but we are trying to find the percent ionization for acid. So we have H3O on top and HClO on the bottom, because this is a reactant and this is a product. And we do that for both, and 0.17% is for a 0.01 molar solution, and 0.054% is for a 0.1 molar. Alright, so now we can deduct that the 0.01 molar solution of HClO has a higher percent ionization. Alright, we are given a graph that says a student titrated 50 milliliters of a 0.1 molar solution of a weak acid, a certain weak acid, with NaOH. So we can write our equation out without knowing the acid as the HA for the acid and its conjugate base. All right, so our first question is, what is the pKa of the acid? We know this from finding the equivalence point, which we'll find when it goes straight up, which is at 25, and that gives us a pH of 8. And what is half of 25 is 12.5. And so our half equivalence point would be around here, and it is a little bit more than 3, so our half equivalence point is equal to our pH of the pKa. So our pKa is 3.2. And to get the Ka and derive it from the pKa, you use the equation Ka equals 10, the antilog, the negative antilog of the pKa, which would give us 6.31 times 10 to the negative 4. We can see that by our equation from getting from pKa to Ka. We need to know the number of moles in NaOH at specific volume and pH, which answers the question, what specific value from this graph is needed in addition to the information in part C above to calculate the molar concentration of NaOH. On to question number 2. Using this graph below, which is right here, we need to identify pKa and pKa, like from here and from here. So pKa1, which we find from our sorry about that, our half equivalence point, I found it to be 2.3 about, and our half equivalence point for the second one would be from, I got it from 16.3, and I have that to get right here, and that would be a pH of 6, which means our pKa is also 6. All right, our next question is to mark the equivalence point and half equivalence points. We already did that because we found our pKa's from that. So equivalence point 2, half equivalence point 2, equivalence point 1, and half equivalence point 1. All right there. All right, part C. It asks us to identify the analyte and the titrant as a strong or weak acid or base. Explain how you identified them. So, it says milliliters of base added, which means base is titrating acid. And we can see it is a very, very weak base because we are shown that it stays after the entire graph is made from at least the first, where we can see the first equivalence point. It only goes up to like a 4.3 for the first equivalence point. All right, so we have already distinguished that it is a weak base, that is the titrant, and it is a strong acid as the analyte, which I wrote right here. Thank you. All right, part D. It says identify and label the species present at the key points. We know that we start off with our acid, which is right around here, which gives us to our weak base, our first base, which is our OH minus. And then we have our second base, which is titrating the H2A right here. And we can derive that from how we know that where is a strong acid and where is a weak base. And then our last task here is distinguishing which one has the highest concentration and the lowest concentration. I said A2- is the highest concentration because we can see in this graph it takes it up to a very high, or it is very large curve for our pH. And a 12 is a high pH. And then HA, I would say, would be it's the strongest acid because it does not allow OH to get very far up. So I put it at the bottom, and I would say our second acid would just be in between. All right, our last question brings us to our buffers, and we are asked how we could make a buffer solution if we only had the weak base NH3 and the acid HCl. We must assume that they have the same concentration unless we are told otherwise. So if we add an extra NH3, it would neutralize all the base of the HCl. Sorry, I think I might have said that HCl was an acid. It is a base. It is a very strong base. And it would produce NH4Cl. This would be our equation. Although this is not balanced, we could add more NH3, which would produce NH4+. It would be our last task, and we could describe how buffer capacity may be increased. You can increase buffer capacity if you increase the molarity of NH3. It just has to have a higher molarity than HCl, then the buffer capacity would be much larger. Thank you, and that is actually all the questions we have for today. If you enjoyed, I'm Kathleen Eustabilar, and I am glad to be teaching you AP Chemistry Unit 8, Acid and Base.